Molecules in a liquid are constantly in motion, and as we've discussed before, the temperature of a liquid is the average kinetic energy of the particles in that liquid. But it's the average. So some particles have more energy than that average, and some particles have less energy than that average. If the particles that have more energy than the average are at the surface, they might actually have enough energy to overcome those intermolecular forces and escape up into the gas phase. So in a liquid, you have intermolecular forces holding things together. Gases do not experience any intermolecular forces. So to go from a liquid to a gas, basically you have to break those intermolecular forces. And that happens when molecules, get enough energy to do so. So if this process happens below the boiling point, it is called evaporation. If it happens at the boiling point, the phase change is called vaporization. And so here you can just see the high energy molecules at the surface escape up into the gas phase. The rate of evaporation will increase as temperature increases, of course, because as temperature increases, more particles will have enough energy to get up into that gas phase. The weaker the intermolecular forces, the faster evaporation will be. This is kind of different than everything else, where, stronger forces give you a higher surface tension, stronger forces give you a higher viscosity. Weaker forces actually give you faster evaporation. And this is, again, because things evaporate when they have enough energy to overcome the forces holding them in the liquid phase. So if those forces are weaker, it takes less energy to overcome them, and it's easier to get up into that gas phase. Liquids that evaporate easily are said to be volatile or volatile. Can be pronounced either way. So, for example, gasoline or nail polish remover are very volatile. That's why they have like an odor, like a very, strong odor, because what you're actually smelling is the particles in that gas phase. Liquids that do not evaporate very easily are non-volatile. So, for example, motor oil, any kind of viscous liquid is pretty non-volatile. It's kind of inverse of viscosity. So thick, viscous liquids, things that are held together very strongly, are not going to evaporate very easily. They're going to be non-volatile. If you have a closed container, the rates of evaporation and condensation will eventually become the same. So when I first put a little stopper in the container, particles are going up into the gas phase, the rate of evaporation is going to be higher than the rate of condensation. But as more and more stuff gets up into the gas phase, it will start to condense back down to the liquid phase. And eventually that rate will become equal, where the rate of evaporation equals the rate of condensation, where for every particle that evaporates, another one condenses. This does not mean that there are equal amounts of vapor and liquid. If you think about what you know about the volumes of gases versus liquids, there's going to be less gas, just because gas takes up so much more volume. But the rate of change in both directions will be the same. So that's what this picture on top is showing here, where in picture A, the rate of evaporation is high. You have a lot of water molecules going up into that vapor phase. In picture B, now that there's some water molecules in the vapor phase, they start to condense, but you can still see there's 3 arrows pointing up and only 2 pointing down. So the rate of evaporation is a little bit higher than the rate of condensation. And then in picture C, there are 3 arrows for each. So the rate of evaporation is equal to the rate of condensation. We have reached dynamic equilibrium. So this video just explains that. I'm not going to play it. Vapor pressure is the pressure exerted by a vapor when it is in dynamic equilibrium with its liquid. So when you have particles up in the vapor phase, they do exert a pressure. That pressure is called vapor pressure. And like rate of evaporation, the weaker the forces, the higher the vapor pressure. The weaker the forces, the easier it is for things to escape their intermolecular forces and get up into that gas phase. So you're going to have more particles in the gas phase, so you're going to have a higher vapor pressure. Same thing, temperature and vapor pressure is the same as evaporation and temperature. As temperature goes up, more particles have enough energy to escape into that gas phase. And so you'd have more particles in the gas phase, and so it would be a higher vapor pressure. So we're going to predict which substance in each of the following pairs would have the larger vapor pressure. So again, if I am rewording this in terms of forces, largest vapor pressure is actually going to be the weakest forces. So for the water versus the methanol, you know, we've seen both of those many times. Methanol just has that one little polar area, and so that's going to be weaker. And so that's going to have a higher vapor pressure. For the methanol versus the propanol, which is this one's propanol, the methanol, again, is going to have the weaker forces because they both have that little polar area, but, you know, the propanol is bigger. So these ones we're going to order from lowest to highest vapor pressure. These are the same ones we did with surface tension. Again, translating that in terms of forces, lowest to highest vapor pressure is going to be strongest forces to weakest forces. So we've seen these ones before. Acetone, we know it has that little polar area right there, and so that's going to be dipole-dipole. Hexane and butane are both dispersion because they are nonpolar. And then the bottom three are the hydrogen bonds. So if I was putting these in order from strongest force to weakest force, water would actually be first. And then ammonia. So water is stronger than ammonia because water, the bond between hydrogen and oxygen is more polar than the bond between nitrogen and hydrogen. And then the propyl alcohol, that's our weakest hydrogen bond because it only has that one little polar area. And then acetone with that dipole-dipole force. And then again, between hexane and butane, hexane is going to be a little bit stronger because it's bigger. And the weakest force, the highest vapor pressure would be butane. So vapor pressure is related to boiling point. There is a temperature at which a liquid is going to reach a point where its vapor pressure is the same as the external pressure, the atmospheric pressure around it. At that point, vapor bubbles can form anywhere in the liquid, not just at the surface. So at that point, it's not just the surface molecules that are escaping up into the gas phase, it could be molecules from anywhere in the liquid. So this is what boiling is. The definition of boiling point is the temperature at which the vapor pressure equals the external pressure. It's kind of a weird definition for boiling point, but that's the definition of boiling point. So if atmospheric pressure goes down, boiling point's going to go down. If atmospheric pressure goes up, boiling point's going to go up. The normal boiling point is at the temperature at which the vapor pressure of a liquid is 1 atmosphere. 1 atmosphere is standard normal pressure at sea level, and so it makes sense that the normal boiling point would be the point at which the vapor pressure equals atmospheric pressure at 1 atmosphere. The lower the pressure, the lower the boiling point. So as I go up the mountains, atmospheric pressure decreases. The atmosphere is thinner, there's not as many particles in the air, and so the atmospheric pressure decreases. So the temperature at which the vapor pressure will equal the atmospheric pressure is lower because the atmospheric pressure is lower. You know, the vapor pressure of water might always be 0.45 at 79 degrees Celsius, but at 1 atmosphere, that it doesn't boil because that's not the atmospheric pressure. But when I'm on the top of Mount McKinley, where the atmospheric pressure is 0.45, that water is going to boil. So it boils at a lower temperature. This video, I will play just the beginning part where he is boiling water simply by creating a vacuum, removing all of the air, all the pressure around it.
Okay, today I'm going to be seeing if you can cook in a vacuum chamber. So first, I'll just put the pasta in water directly in the vacuum chamber, reduce the pressure until the water starts boiling, and see if we leave it in there for the allotted amount of time, see if it cooks the pasta enough that we can eat it. And then if that doesn't cook the pasta, I'll add a heat source to it. So I'll put it on a unit in the vacuum chamber so that it does have a constant heat source, and see if then we can cook the pasta in the vacuum chamber. You might be surprised by the results. Okay, we're gonna be cooking penne pasta today. Okay, first, cooking pasta in a vacuum chamber with no heat source. 3, 2, 1. So you can see the dissolved air starting to come out of it already. It's not quite boiling yet. See, it already looks like it's on the stove, about to boil. That white foam at the top. Okay, we're at full vacuum now. We've got some pretty good boiling going on in there now. You can see the sporadic bubbles that pop up every once in a while. So I've heard a lot of people say in the comments section that they don't think it's actually boiling in the vacuum chamber. They think it's just releasing the dissolved gases in the water. And while it is true that it does release dissolved gases, it is actually boiling. So boiling is defined as when the vapor pressure of the liquid is greater than the pressure around it. And so once that happens, that's when it boils. So when you reduce the pressure around it, even room temperature water has a vapor pressure high enough to start boiling. So it is actually a defined thing what boiling is. It's not just when there's bubbles in liquid. Okay, we've got a pretty good rolling boil going now. So I'm gonna leave it going for around 11 minutes and see if our pasta is cooked after this. Okay, it's been about 11 minutes. Let's let in the air and see. First, let's see how cold that water is, and then let's see if the pasta is tender at all. Okay, letting in the air, 3, 2, 1. Okay, still cold and crunchy pasta. So no, I did not cook the pasta.
Okay. So explaining the difference between the boiling points between formaldehyde and ethane. Formaldehyde has that polar area, so it's going to have dipole-dipole forces. Ethane is nonpolar, so that's only going to have dispersion forces. So you can see the boiling point, they're both very low, but the boiling point of formaldehyde is much higher than that of ethane because it has the stronger forces. Stronger forces is going to make it harder for stuff to go up into that vapor phase, so it's going to boil at a higher temperature. Ranking these from lowest to highest boiling point, again, you first need to figure out what forces are present. So we've seen methanol a lot. We know that methanol has that little area of hydrogen bonding. Carbon dioxide we know is nonpolar, so that's dispersion. Water, we know hydrogen bonds. Krypton is just a singular, atom, so that's going to be nonpolar. We're going to call that dispersion forces. And then ammonia, also hydrogen bonds. So ranking from lowest to highest boiling point, if we translate that in terms of forces, what we are saying is we're going from weak to strong. The weakest forces have the lowest boiling point. The strongest forces have the highest boiling point. So the weakest force here is going to be our krypton, because that's dispersion and that's the smallest. And then, carbon dioxide, I don't know, CO3, carbon dioxide. And then between the hydrogen bonds, methanol would be the lowest because it only has that one little polar area. And then ammonia, and then water. And again, ammonia is weaker than water because the NH bond is less polar than the OH bond.